Welcome to Night Lesson. Relax and learn along the way. Intro. What we cannot see. Have you ever gazed up at the sky on a clear night and felt as if you were looking into infinity? The moon, a gentle, silver companion. The countless stars, scattered like fine diamond dust on dark velvet. Planets, tracing their orbits as calm, steady points of light. Perhaps even the delicate veil of the Milky Way, a luminous band of billions of suns. This picture feels complete, majestic, and all-encompassing. It seems as though the entire universe is unfolding before us. But what if this breathtaking scenery, everything we have ever seen with our eyes or our most powerful telescopes, is just a fleeting shimmer of the true reality? Imagine that all the familiar matter, the atoms that you and I are made of, the rocks beneath our feet, the air we breathe, the gases that burn in the hearts of stars, and light itself. All of this together makes up only about 5% of the entire cosmos. Just 5 tiny percent. Everything that humanity has ever touched, mapped, weighed, or named in its entire history is merely the visible tip of an immeasurably vast, invisible iceberg. So what fills the overwhelming 95% that eludes our sight? It is an invisible scaffold, a hidden fabric that both holds everything together and pushes it apart. Scientists divide this mysterious majority into two enigmatic components. About 27% they call dark matter. It is like a silent, invisible architect whose gravity shapes galaxies and keeps them from flying apart as they rapidly rotate. The remaining 68% is even more puzzling. Dark energy, a gentle but relentless force that stretches space itself, causing the universe to expand at an ever-accelerating rate. These invisible worlds do not emit light, they do not absorb it, they do not reflect it. They do not interact in any way we know with the electromagnetic spectrum that reveals reality to our senses and instruments. They are simply there, silent, immense, and omnipresent. So how can we be so sure they exist? And how do we search for something that hides itself so masterfully? Let us journey together. A journey not to the shining stars, but into the quiet, invisible currents that fill the space between them and determine the fate of the entire cosmos. Chapter 1. The Man No One Believed. Fritz Zwicky. The journey into the invisible does not begin with a modern super telescope, but in the 1930s, with a man whose mind was as unconventional as his ideas. His name was Fritz Zwicky, a Swiss-American astrophysicist who worked at the California Institute of Technology. He was known for his brilliant, but also contentious nature. A man who dared to ask questions others did not even dare to think, and who was not afraid to challenge conventions that were considered unshakable. In 1933, Zwicky turned his attention to a distant, majestic structure in the night sky, the Coma cluster of galaxies. Imagine this assembly, not as a handful of stars, but as a cosmic metropolis of over 1,000 individual galaxies. Each of these galaxies, a universe of billions of suns in its own right, dances within a common gravitational field. This enormous cluster is an unimaginable 300 million light-years away from us, a faint, misty patch for the telescopes of that era. But for Zwicky, it was a laboratory for testing the fundamental laws of the universe. With meticulous patience, he measured the velocities of the individual galaxies within the cluster. He observed how they moved around each other, how they traveled through their shared space. And in doing so, he encountered a deep, unsettling puzzle. The galaxies were moving much, much too fast. Their speeds were so enormous that the visible mass of the entire cluster, all the stars, all the luminous gas he could see and measure, would never be enough to hold them together. Imagine a group of dancers holding hands and spinning in a circle. The faster they spin, the stronger their grip must be to keep from flying apart. But the galaxies in the Coma cluster were spinning with a velocity for which there was no visible anchor. According to the laws of gravity, they should have long since been flung in all directions into empty space. The cluster should have dispersed like smoke in the wind. But it didn't. It was stable. Zwicky did the math. He used what is known as the Vera theorem, a mathematical tool that relates the kinetic energy of a system to its potential or gravitational binding energy. His calculations were clear and shocking. To hold the galaxies together at these speeds, the Coma cluster would have to contain about 400 times more mass than it showed in the form of stars and luminous matter. Where was this missing mass? Zwicky came to a radical conclusion. There had to be another kind of matter. An invisible substance that emits no radiation, reflects no light, but still exerts a tremendous gravitational force. He called it dunkle materie, or dark matter, an invisible web that permeates the entire galaxy cluster, holding it together with its silent but immense power. But the scientific community was not ready for such a revolutionary idea. Zwicky's conclusion was met with deep skepticism, often even ridicule. It was dismissed as a measurement error, an eccentric fantasy of a colleague already considered difficult. For nearly 40 years, his discovery was largely ignored. The idea of an invisible matter making up the bulk of the universe was simply too strange, too unbelievable. So Zwicky's premonition of an invisible world lay unheard at the margins of science for decades. His data was like a soft whisper from the depths of the cosmos, which most simply failed to hear. But the whisper had not vanished. It was merely waiting patiently for new ears, new instruments, and new eyes to be ready to listen and to take up the search for the invisible once more. Chapter 2. The Woman Who Remeasured the Universe, Vera Rubin. The whisper Zwicky had heard found its echo in the late 1960s and early 1970s. It reverberated through the quiet, cool domes of observatories, where a new generation of astronomers was measuring the sky with unprecedented precision. On those nights, under the infinite velvet of the Arizona sky, astronomer Vera Rubin and her colleague Kent Ford were listening in their own way. Their instrument was not a giant ear, but a highly advanced spectrograph, a device that splits the light from distant stars into its rainbow of colors. Their work was marked by a meditative patience. Hour after hour, they pointed the telescope at a single, distant spiral galaxy, often our majestic neighbor, the Andromeda Galaxy. They collected the light from tiny, luminous gas clouds and star clusters orbiting far out on the outermost edges of the galactic disk. The question they sought to answer seemed simple and followed a familiar logic. Just as the planets in our solar system move more slowly the farther they are from the sun, so too should the stars in a galaxy behave. Most of the visible matter, the billions of shining stars, is concentrated in the bright center of a galaxy. The stars on the edge, far from this gravitational center, should be moving at a leisurely pace, held by an ever-weakening pull. This was the expectation, based on the fundamental laws of gravity we have known since Kepler and Newton. But the universe had a different melody in mind. As Rubin and Ford analyzed their data, a picture emerged that contradicted all expectations. The light of the stars they analyzed revealed its speed through the Doppler effect. If a star moved towards us, its light was slightly shifted to the blue. If it moved away, it shifted to the red. From the magnitude of this shift, they could calculate the star's speeds with incredible accuracy. And what they saw was astonishing. The stars in the outer regions of the Andromeda Galaxy were not moving more slowly. On the contrary, they were racing around the center at nearly the same breathtaking speed as the stars much farther in. At first, they thought it was a measurement error. Perhaps it was a peculiarity of the Andromeda Galaxy. So they repeated their measurements. Night after night, galaxy after galaxy. They observed over 60 more spiral galaxies, large and small, near and far. The result was always the same. The rotation curves, The graphs that plotted the speed of stars against their distance from the center were not falling. They were flat. Like an infinitely long, straight line, they extended to the outermost limits their instruments could detect. These flat curves were more than just a scientific curiosity. They were irrefutable proof. Proof that the visible matter, all the stars, all the gas and dust, could only be the tip of the iceberg. For the outer stars to orbit so quickly without simply being flung into the void of intergalactic space, there had to be a vast, invisible mass. An additional source of gravity, holding everything together. Rubin concluded that every galaxy must be enveloped in a huge, spherical halo of this mysterious substance. An invisible sphere, surrounding the luminous disk like a protective cocoon, its mass exceeding that of the visible stars by 10 or even 100 times. Vera Rubin's discovery was a quiet revolution, which she pursued with unshakable persistence. Her path had not been an easy one. As a woman in the male-dominated world of 20th century astronomy, she had to fight against constant resistance. She was denied admission to graduate programs, and the famous Palomar Observatory was long closed to her simply because it had no women's restroom. But her fascination with the motion of the stars, which had gripped her as a young girl looking out her window in Washington, D.C., never left her. She was not loud, but she was persistent. She let the data speak for itself, and its language was unmistakable. Vera Rubin passed away in 2016. Despite the fundamental importance of her work, which changed cosmology forever and laid the foundation for our modern understanding of the universe, she was never awarded the Nobel Prize. But her legacy is embedded in every flat rotation curve measured since. She had not only remeasured the universe, she had opened our eyes to the 90% that lies hidden. Her work confirmed that Zwicky's whisper was real. The mystery of the missing mass was no longer a vague conjecture, but a fact secured by observation. The question was no longer if dark matter existed, but what it was. And so, her discovery opened the door to an even deeper, more fundamental mystery. Chapter 3: The Bullet Cluster, the Strongest Proof. In the deepest reaches of the cosmos, where time is measured in eons, a spectacle of unimaginable force and silent elegance is unfolding. It is not a sudden explosion, not a loud bang, but a collision in cosmic slow motion. Imagine two vast collections of galaxies, galaxy clusters, each a universe of stars, gas, and dust, drifting toward one another over hundreds of millions of years. Driven by the relentless force of gravity, they move toward each other until they finally merge. Such an encounter took place about 150 million years ago, and the light from this event reached us in 2006. Astronomers call this cosmic structure 1E0657-558, but it is better known by its more vivid name, the Bullet Cluster. When two such giants collide, one would expect their components to mix and be slowed down by mutual attraction and friction. In particular, the huge clouds of intergalactic gas, which make up most of the normal, visible matter in the clusters, should crash into each other like two immense waves. They would heat up, become compressed, and form a turbulent, glowing region at the center of the collision. The stars and the galaxies themselves are so small compared to the distances between them that they would mostly pass through each other unscathed, but they too would be slowed down by the immense gravity of the entire system. In the end, the center of mass should be located exactly where the visible matter is most densely concentrated, at the heart of the collision. But when telescopes on Earth and in space turned their gaze to the Bullet Cluster, they saw something completely unexpected. They looked not with a single pair of eyes, but with many. First, the Chandra X-ray Observatory looked. Its eyes are specialized to see extremely hot gases that glow in X-ray light. And indeed, just as predicted, Chandra found a huge, glowing cloud at the center of the collision. In the colored representations made by astronomers, It often appears in bright pink or red, a massive accumulation of gas heated to millions of degrees by the impact. Here, at the center, was the majority of the baryonic, the familiar, matter. Up to this point, everything seemed to match expectations. But then other telescopes, like the Hubble Space Telescope, turned their view to the same patch of sky. They were not looking for light coming from the collision itself, but for something much more subtle. The way the cluster's mass was bending the light from even more distant galaxies in the background. This phenomenon, the gravitational lensing effect, is a direct consequence of Einstein's general theory of relativity. Mass curves space, and light follows this curvature. By analyzing the tiny, systematic distortions in the appearance of thousands of background galaxies, one can create a map of the mass distribution in the foreground, completely independent of whether this mass shines or not. The map that emerged from these observations was breathtaking and contradicted everything that had been expected. The greatest concentrations of mass were not at the center where the hot gas was glowing. Instead, there were two enormous centers of mass located on either side of the gas center. It was as if two invisible clouds had passed through the collision unharmed. They had raced ahead of the hot gas, almost as if they hadn't noticed the collision at all. The smaller of the two clusters, which had shot through the larger one like a bullet, gave the system its name. Here was the proof, as clear and distinct as a footprint in the snow. The visible matter, the gas, had interacted and was left behind in the center. But the invisible matter, which accounted for the vast majority of the total mass, had barely interacted. It had passed through like a ghost through a wall. It felt only gravity, not the friction or other forces that slowed down the gas. The separation was complete. On one side, the luminous, hot cloud of normal matter. On the other side, having moved ahead and detectable only by its gravity, the enormous halos of dark matter. This was the moment that put alternative theories like modified Newtonian dynamics, MOND, in serious trouble. These theories proposed that there was no dark matter, but that the law of gravity itself acts differently at large distances. But if that were true, the gravitational lens should have shown the greatest mass where the most visible matter was, at the center with the hot gas. The bullet cluster showed the exact opposite. The mass and the light were separated. It was as if the cosmos itself had conducted an experiment for us, to lift one of its deepest veils. The collision of two galaxy clusters became a cosmic particle accelerator, separating the dark matter from the ordinary matter and allowing us to observe them separately. The smoking gun had been found. The existence of dark matter was no longer an indirect inference, but a direct observation. The ghost clouds, gliding undisturbed through the cosmic chaos, confirmed the suspicions of Zwicky and Rubin in the most spectacular way imaginable. The question was no longer whether it existed, but what its fundamental nature might be. Chapter 4, What Could It Be? The Candidates. The question that now hung in the air, hovered heavy and silent like a fog between the galaxies. If this invisible mass exists, if it holds the universe in its hand, what exactly is it? The scientific community, now convinced of its existence, began to assemble the suspects in a cosmic lineup. There is no definitive answer, only a series of fascinating possibilities, of candidates that each paint a different universe. The first, and, for a long time, favored candidate bears an almost playful name, WIMP, an acronym for Weakly Interacting Massive Particle. Imagine a particle that is perhaps 100 times heavier than a proton, the building block of our atomic nuclei. It possesses considerable mass, but it is a phantom. It does not feel the electromagnetic force, which is why it neither emits nor reflects light. It also ignores the strong nuclear force that holds atomic nuclei together. It participates in only two fundamental forces, the omnipresent gravity, through which it forms galaxies, and the weak nuclear force, the force responsible for certain forms of radioactive decay. The truly remarkable thing about WIMPs is something physicists call the WIMP miracle. Calculations about the early universe, that unimaginably hot and dense state in the first fractions of a second after the Big Bang, reveal a fascinating picture. In this primordial soup, particles were continuously created and annihilated. As the universe expanded and cooled, there was a moment, about 10 billionths of a second after the beginning, when WIMPs could no longer find a partner for mutual annihilation quickly enough. They froze out of thermal equilibrium. This means they decoupled from the rest of the matter and have existed ever since as a relic of that first epoch. The miracle is that, if one assumes a particle with the properties of a WIMP, the calculated amount that would have survived this process corresponds almost exactly to the amount of dark matter measured today. The so-called relic density, a value astronomers quantify as omega h superscript 2, is almost equal to 0.12. Fits like a key in a lock. It seemed too perfect not to be true. But there are other, equally tantalizing candidates. One of them is the axion. Unlike the heavy WIMP, the axion is an ultralight particle. Its mass is tiny, perhaps only a billionth of the mass of an electron. Axions were not invented to solve the mystery of dark matter. They emerged as a theoretical solution to a completely different problem in particle physics related to the strong nuclear force. The fact that they were later also identified as an ideal candidate for dark matter lends them a special elegance. Instead of flying through space as individual, heavy particles, axions are imagined more as a vast, coherent field that permeates the entire universe, like a subtle wave oscillating with an unimaginably long wavelength. Their origin is traced back to a moment in the early universe when a fundamental symmetry, the Pecci-Quinn symmetry, broke. This break, like the sudden freezing of water into ice, would have flooded the universe with these light particles. Experiments like ADMX and Haystack are trying to detect these particles by using huge magnetic fields and microwave cavities to make the axion field ring, producing a tiny, detectable photon. A third path leads us to a relative of known particles, the sterile neutrino. We know of 3 types of neutrinos. They are incredibly light, almost massless, and interact so weakly that trillions of them stream through your body every second unnoticed. The sterile neutrino would be a 4th, even shyer type. It would not even participate in the weak nuclear force, as its known cousins do. Its only connection to our world would be gravity. It would be the ultimate hermit of the particle zoo, a ghost squared. Its existence would be a subtle extension of the standard model of particle physics, a less radical assumption than that of a completely new type of particle like the WIMP. And then there is a 4th possibility, which takes us from the world of subatomic particles to that of vast cosmic objects, primordial black holes. These are not black holes formed from the collapse of massive stars. Rather, they are ancient relics from the very first second of the universe. Back then, the universe was so dense that tiny fluctuations in density were enough to cause some regions to collapse directly into black holes. These could still exist today, coming in a wide range of masses. The mass window of interest for dark matter lies in the range of 10 to the 17th to 10 to the 23rd kilograms, from the mass of a large asteroid to that of a small moon. For a long time, this idea was considered unlikely, but it experienced a renaissance when gravitational wave observatories like LIGO detected black holes with masses that were not easily explained by stellar processes. Could these be the descendants of those primordial objects? For candidates, for completely different conceptions of the hidden substance of the cosmos. A heavy, ghostly particle from the initial heat of the universe. An ultralight, omnipresent field born from a symmetry break. An extremely shy relative of a known particle. Or ancient, dark objects that have been drifting through the void since the dawn of time. Each of these hypotheses has its own beauty, its own strengths and weaknesses, and each of them requires a different kind of search, a different method to listen into the darkness and find an answer. The hunt had just begun. Chapter 5: The Cosmic Web, Dark Matter as the Blueprint. When we look at the universe in its entirety, far beyond the confines of our own Milky Way, an unexpected pattern reveals itself. It is not a random collection of stars and galaxies distributed evenly in space. Instead, we see a structure of unimaginable scale, a filigree tapestry of galaxy clusters and long, thin filaments of matter stretching over hundreds of millions of light years. We call this structure the cosmic web. The brightest and densest parts of this web are the nodes. Here, thousands of galaxies clump together into enormous superclusters, places of intense gravitational attraction. From these nodes extend long, luminous strands, the filaments. Like the silk threads in a spider's web, they connect the nodes. Along these filaments, galaxies are strung like pearls on a string, flowing slowly but steadily toward the denser nodes. And between these luminous structures lie the voids, the great cosmic empty spaces. These are vast, nearly spherical bubbles with diameters of 200 to 300 million light years, where almost no matter is found. They are islands of the deepest silence and darkness, where the density of matter is far below the cosmic average. It takes light hundreds of millions of years just to cross one of these voids, more time than complex life has existed on Earth. For a long time, it was a mystery how such a grand architecture could have formed. The visible matter alone, the stars, the gas, the dust, does not possess enough gravity to assemble itself into such vast, yet delicate structures in the 13.8 billion years since the Big Bang. The gravity of visible matter is simply too weak. It would have left behind a much more uniform distribution, a diffuse fog with no clear structure. This is where dark matter enters the stage, not as a candidate for a particle, but as the invisible architect of the universe. To test this hypothesis, scientists turned to supercomputers. They created digital universes to simulate the evolution of the cosmos from the very beginning. One of the most famous of these was the Millennium simulation from 2005. Researchers fed the initial conditions of the universe, as we know them from the cosmic microwave background, an almost uniform state with tiny density fluctuations, into the computer. They programmed the laws of physics, especially gravity, and then let time run and fast forward. In the simulation that contained only visible matter, almost nothing happened. The matter clumped a little, but no web-like structure emerged. The result was a largely homogeneous universe that bore no resemblance to what we observe. Then they added the crucial ingredient, a large amount of cold dark matter. Cold here means that its particles move slowly. And crucially, it is almost collisionless. While particles of normal matter interact with each other, heat up, and create pressure that counteracts gravity, the particles of dark matter feel only gravity. They can simply pass through one another. With this ingredient, everything changed. In the simulation, the dark matter immediately began to respond to the tiny initial density fluctuations. Wherever the density was just a tiny bit higher, more dark matter gathered, further increasing the gravity there. It was a self-reinforcing process. Over billions of years, the dark matter formed a vast, invisible scaffold, a web of filaments and nodes. And the normal, baryonic matter? It simply followed. Like iron filings aligning with the field lines of an invisible magnet, the gas of the early universe was pulled into the gravitational wells created by the dark matter. It collected in the filaments and fell into the nodes. Only there, in the protective embrace of the dark matter, did the density become high enough to form the first stars and galaxies. More recent simulations like Illustrious TNG have refined this picture even further by including the complex physics of gas, star formation, and black holes. But the result remains the same. Only a universe composed of about 85% dark matter evolves into the cosmic web that we map with our telescopes today. The simulations agree with observations in minute detail, even down to the subtle patterns of the so-called baryon acoustic oscillations, echoes of sound waves that traveled through the early universe and left behind a preferred distance between galaxies. So dark matter is not just a strange anomaly that holds galaxies together. It is the foundation of everything. Without this invisible scaffold, no galaxies would have formed. Without galaxies, there would be no stars. Without stars, no heavy elements. And without heavy elements, no planets, no water, no life. The large-scale structure of the universe is a silent but overwhelming testament to the existence and power of something we cannot see. This cosmic map, drawn with invisible ink, not only tells us where the galaxies are, it also tells us where we must look, where we must listen, to perhaps finally catch a glimpse of the architect itself. Chapter 6: The Great Search, Experiments and Detectors. The invisible ink of the cosmic web has drawn the map. Now it is up to humans to forge the tools to decipher this script. The silent but omnipresent gravitational effect of dark matter is the starting point. But to understand its true nature, one must touch it, see it, or create it. From this necessity, three major strategies have emerged, three paths that lead deep into matter, high into the cosmos, and into the fundamental energies of the universe. The first path is the most direct and perhaps the most patient. It is the path of direct detection. The idea behind it is almost elegantly simple. If we are surrounded by an ocean of dark matter particles, WIMPs, then every now and then, one of these particles should collide directly with an atomic nucleus here on Earth. Imagine a single, tiny billiard shot in the heart of an atom. An invisible particle strikes an atomic nucleus and gives it a barely perceptible nudge. It is this tiny tremor, this atomic echo, that scientists hope to measure. The challenge, however, is monumental. WIMPs, according to theory, interact only via the weak nuclear force and gravity. This means they are incredibly elusive. A single WIMP could pass through the entire Earth, from one pole to the other, as if it were empty space, without ever interacting with a single atom. So, to have a chance of observing one of these countless billions of possible collisions, you need huge, extremely sensitive detectors and, above all, silence. Absolute, undisturbed silence. This silence is found deep underground. One of the quietest places on our planet is in the former Homestake gold mine in South Dakota, nearly a mile beneath the surface. There, shielded by 1,478 meters of solid rock that filters out the constant rain of cosmic rays from space, lies the heart of the Lux Zeppelin experiment, or LZ. In a giant titanium tank, 10 tons of ultra-pure liquid xenon float, cooled to a temperature where the atoms move only sluggishly. If a WIMP were to strike a xenon nucleus, it would create a tiny flash of light and a handful of free electrons. Highly sensitive sensors, called photomultipliers, wait in the dark to catch precisely this faint glow, this whisper from the dark sector. The sensitivity is so high that researchers hope to detect just a single event per year in 1,000 kilograms of xenon. On the other side of the Atlantic, deep beneath the Gran Sasso Massif in Italy, a similar experiment called Xenon NT listens in the darkness. And in other parts of the world, experiments like CRES-SD use crystals of tungsten or CDMS uses germanium, in the hope that dark matter might have a preference for interacting with heavier or lighter nuclei. But so far, the result of all these efforts is a deep, unbroken silence. Not a single WIMP has shown itself beyond a doubt. Yet this silence is not a defeat. With each day the detectors run without a signal, scientists draw the circle tighter. They can rule out what properties dark matter does not have, setting ever stricter upper limits on its interaction strength. The search becomes a process of patient elimination. The second path leads away from the Earth, out into orbit. It is the path of indirect detection. If WIMPs are their own antiparticles, as many models predict, then when they meet, they should annihilate each other in a process called annihilation. From this tiny burst of pure energy, known particles would then emerge, including gamma rays with a very specific, characteristic energy. These gamma rays would be like a luminous signature, a telltale fingerprint of dark matter. High above our heads, NASA's Fermi Gamma Ray Space Telescope circles, constantly scanning the sky for such signals. Its gaze is particularly focused on places where the density of dark matter should be especially high, the center of our Milky Way or dwarf galaxies that orbit it. If Fermi were to discover a clear gamma ray line, an excess of gamma rays at a very specific energy, it would be revolutionary proof. So far, the telescope has discovered many fascinating phenomena in the high-energy universe, but the unambiguous signature of WIMP annihilation is also missing here. Again, certain masses and models for dark matter are ruled out, and the map of what is possible becomes a little less blank. The third and final path is the boldest. It follows the motto, if we can't find dark matter, we'll create it ourselves. This is the domain of particle accelerators, chief among them the Large Hadron Collider, the LHC, at CERN. In its 27-kilometer ring tunnel beneath the Swiss-French border, protons are accelerated to unimaginable speeds and made to collide. In these tiny fireballs, which for a fraction of a second recreate the conditions shortly after the Big Bang, dark matter particles could also be created. Since they are so weakly interacting, they would simply pass through the huge detectors of the LHC unnoticed. So you couldn't see them directly, but you could notice their presence by what is missing. After a collision, the detectors precisely measure the energy and momentum of all the particles produced. If the sum on one side does not match the sum on the other, if energy and momentum have seemingly vanished, then this points to an invisible particle that has flown away. This missing transverse energy is the hoped-for signal. In the current Run 3 of the LHC, the search for exactly this signature is being conducted with even higher energy and precision. But as on the other two paths, silence has prevailed here as well. 3 major strategies, 3 monumental efforts, all aimed at the same goal. Every experiment that remains silent is a quiet but valuable answer. It is a signpost in a labyrinth, telling us which paths do not lead to the destination. And so the search is refined, becomes more precise, and humanity's gaze turns to new horizons, listening for even finer echoes in the silence of the cosmos. Chapter 7, Dark Energy, the Even Greater Unknown. The year 1998. In the observatories of the world, under the clear skies of Chile and Hawaii, the grand story of cosmic expansion seemed to be a clear, almost completed narrative. It was known that the universe had been expanding since the Big Bang. Gravity, it was generally assumed, acted as an invisible brake on this expansion. All matter, both visible and dark, pulled on each other and was expected to slow down the flight of the galaxies over the eons. The only remaining question seemed to be, is the brake strong enough to eventually stop the expansion and reverse it, or will it slow down forever but never come to a complete halt? 2 independent teams of astronomers, led by Saul Perlmutter on one side and Brian Schmidt and Adam Rees on the other, set out to measure exactly this deceleration. Their tools were the most reliable beacons in the cosmos, Type 1 amps supernovae. These special stellar explosions occur when a white dwarf star in a binary system siphons matter from its companion until it reaches a critical mass and explodes in a thermonuclear detonation of consistently reliable brightness. They are the standard candles of cosmology. If you know their true luminosity, you can accurately calculate their distance from their apparent brightness in the earthly sky. The astronomers pointed their telescopes to the most distant corners of the universe, searching for these exploding stars in galaxies billions of light years away. The light from these supernovae was a message from the deep past. The farther away they were, the further back in time the researchers were looking, and what they found did not fit the picture. The most distant supernovae, those from a time when the universe was younger, were fainter than they should have been. They were not just a little fainter, but significantly so. There was only one explanation, as incredible as it sounded. The explosions were farther away than the prevailing models predicted. This meant that the expansion of the universe, in the time it took their light to reach us, had not slowed down, but had accelerated. This discovery, for which the three researchers would receive the Nobel Prize in Physics in 2011, turned cosmology on its head. An unknown force had to be at work, a kind of anti-gravity, giving the universe an unstoppable push. They called it dark energy, and it is immense. Today's measurements suggest that it makes up about 68% of the total energy density of the universe. While dark matter, with its gravity, acts like a cosmic glue holding galaxies and galaxy clusters together, dark energy is a repulsive force that drives space itself apart. Dark matter pulls things together. Dark energy pushes them apart. Suddenly, an old idea of Albert Einstein's was remembered. In his equations for general relativity, he had included a cosmological constant, symbolized by the Greek letter lambda. He needed it to describe a static, eternal universe that neither expanded nor collapsed. When Edwin Hubble proved the expansion of the universe, Einstein called the constant his greatest blunder and struck it out. But now, decades later, it was making a triumphant return. This constant describes an energy inherent to the vacuum of space itself, a property of nothingness that has a constant, repulsive effect. Perhaps Einstein's greatest mistake hadn't been a mistake at all. But the story isn't over yet. Is this energy truly constant? Or does it change over time? Models like quintessence or the even more exotic phantom energy play with this idea. If dark energy increases, the future of the universe could end in a big rip. In perhaps 22 billion years, the expansion would become so strong that it would first tear apart galaxy clusters, then galaxies, then planetary systems, and finally even atoms. It is a distant, almost unimaginable fate. And just recently, in 2024, a sky survey called DESI provided the first, tentative hints that the cosmological constant may not be so constant after all. The mystery of dark energy is even deeper, even more far-reaching than that of dark matter. It is a question not just about the contents of the cosmos, but about the fundamental nature of space and time itself. And with each new observation, we continue to listen into this expanding silence, searching for an answer to the question of what drives our universe. Chapter 8: Heretical Theories. What if dark matter doesn't exist? What if we are on the wrong path? What if the great cosmic mystery lies not in what we cannot see, but in the laws we thought we understood? This question is not an admission of failure, but a quiet, courageous knock on the door of our knowledge. It is a thought experiment that leads us down a shadowy, less traveled path of cosmology, away from the search for new particles and toward a reevaluation of our most fundamental assumptions about gravity. In 1983, the Israeli physicist Mordechai Milgram proposed such a heretical idea. His theory, known as MOND, modified Newtonian dynamics, was elegant in its simplicity. Milgram wondered, what if Isaac Newton's law of gravity, which works so flawlessly on Earth and in our solar system, changes its form over the vast, empty distances within a galaxy? His hypothesis was that gravity behaves differently at extremely low accelerations. He defined a fundamental threshold, a value known as Milgram's parameter, A. This value is tiny, about 1.2 times 10 to the minus 10 meters per second squared. It is an acceleration so unimaginably small that we experience it nowhere in the solar system. However, in the outer, star-poor regions of a galaxy, where the pull of the center is felt only as a gentle whisper, the accelerations of the stars fall below this critical value. And right here, Milgram proposed, the game changes. Below this threshold, the force of gravity no longer weakens with the square of the distance, as Newton taught. Instead, it decreases much more slowly. The stars at the edge of a galaxy feel a stronger pull than they should, and therefore move faster, exactly as fast as Vera Rubin had observed. With this one bold adjustment, Mond could perfectly explain the flat rotation curves of galaxies without needing a single particle of dark matter. The theory even naturally predicted an observed relationship, the Tully-Fisher relation, something with which standard dark matter models often struggle. But this elegant path has its own deep shadows. While Mond works astonishingly well at the level of individual galaxies, the theory fails when one looks at even larger structures. In the vast collections of hundreds or thousands of galaxies, the galaxy clusters, the modified gravity is not enough to hold the fast-moving galaxies together. Here, too, a large amount of invisible mass seems to be missing, even for Mond. And the strongest evidence for dark matter, the bullet cluster, remains an insurmountable obstacle. There, we see the effect of gravity separated from the visible matter, a phenomenon that a modification of gravity alone cannot explain. Nevertheless, the spirit of inquiry has not been laid to rest. More complex theories have grown out of Milgram's original idea. There is Tevis, a relativistic extension of Mond developed by physicist Jacob Bekenstein to reconcile the theory with Einstein's general relativity. And there are even more radical proposals, like the emergent gravity of Eric Verland, which postulates that gravity is not a fundamental force at all, but an entropic phenomenon that arises from the information in the fabric of space-time. Most physicists today still hold to the concept of dark matter. The evidence from so many different areas, from the cosmic microwave background to gravitational lensing to the formation of structures, paints a coherent, albeit incomplete, picture. But the fact that an idea as simple as Mond can describe the dynamics of galaxies so precisely whispers a constant reminder to us. We must never be too sure of our assumptions. The possibility that dark matter could be an illusion, a phantom born from our incomplete understanding of gravity, must be taken seriously. It keeps the door open for a revolution in our thinking, one that may still be to come. Outro. The greatest mystery of all. We now stand at the end of our journey, but not at the end of the story. We have followed tracks in the sands of cosmology, listened to echoes from the depths of time, and observed shadows cast by something we cannot see. The sum of all these observations is an insight as simple as it is profound. We know that there is something holding the galaxies together and shaping the universe. We call it dark matter, but we do not know what it is. In the coming years, we are turning our ears and eyes even deeper into space. Deep underground, in the LZ experiment, sensitive detectors listen in perfect silence for the faintest whisper of a collision, the touch of a WIMP particle. High above us, the Euclid satellite is mapping the distribution of galaxies with tireless precision, measuring the subtle distortions of light to reveal the invisible structure of the cosmos. And soon, CMB S4, a network of telescopes, will study the afterglow of the Big Bang with unprecedented accuracy, searching for the fingerprints that dark matter left in the cradle of the universe. But the possibility remains that we are looking at the puzzle from the wrong side, that we are chasing ghosts, while the answer lies hidden in the laws of gravity itself. This is perhaps the greatest lesson of this search. Science is not a fixed building of unshakable truths, but a constant process of questioning, doubting, and rediscovering. The willingness to be completely wrong is not a weakness, but the greatest strength of the human spirit. The universe is not a finished map that we just need to unroll. It is an open book, and we have only just read the first few pages. Every answer we find only reveals deeper, more beautiful questions. And so the search continues, a silent, patient hunt for the nature of reality itself, hiding in the dark.
That was today's night lesson. Thank you for listening. If you'd like to see more videos like this, please leave a like and subscribe to the channel. Good night and sleep well.